Hello there. Welcome back from the Thanksgiving break. I am not going to be able to be in class today, so I thought I would record this lecture, and then we can talk about this Wednesday if you have any questions about it. So before the break, we started talking about dot products and orthogonality. We'll review some of that now and then move on and talk about orthogonal sets in section 6.2, getting ready for the Gram-Schmidt process. So remember how we define the dot product. We define the dot product of two vectors in Rn to be taking the corresponding components, this one and that one, multiplying these two together. Keep doing that all the way through, taking all those products and then adding them together. And so we can write it in that form where we multiply the corresponding components and add them together. We can condense it in terms of the sigma notation given here. And if you remember, part of what we did with the dot product is we encoded information about lengths and angles. And so if you remember, the magnitude of a vector is just going to be the square root of the dot product of the vector with itself. Okay, and we also have a number of algebraic properties here that when we talk about two vectors and taking their dot product, it's really the same as taking this matrix product here. Okay, and so we get a lot of properties of dot product for free that way. And so we see those in this theorem 1. Okay, where really the first A, B, B prime, C really just follow from the fact that they can be realized as matrix products. This one is just for the real numbers, if you remember, because that means when I take the dot product of U with itself, what I'm doing is means I'm squaring each component and adding it together. And in the real numbers, when I square something, it's always non-negative. Okay? And in order for the dot product of a vector with itself to be 0, it means that the vector itself had to be the 0 vector. Again, this is encoding lengths, and because lengths are always positive or non-negative, when I multiply by a scalar, when I pull that out, don't forget I need to take the absolute value of that scalar. So that's sort of a review of things. I said it also encoded information about angles, and that's true. The one angle that we're most concerned about is a 90-degree angle, and we talked about orthogonality. And so what we say is that two vectors U and V are orthogonal if their dot product is 0. Okay? Now, one of the things we're interested in is orthogonal complements of subspaces. And so we say a vector is orthogonal to a subspace W if it's orthogonal to every vector in that subspace. Okay. We have a way of calculating that. Theorem 1, we had shown previously that really all we need to do is to show something is orthogonal to every vector in the subspace. All we need to do is check this for a finite generating set, show it's orthogonal to every element in a finite generating set. So that makes it more computationally effective. And so we take a look at all vectors that are orthogonal to a subspace, and that's going to be W perp, which is a set of all vectors orthogonal to W. And we can define it using set notation, all vectors such that V dot W is equal to 0 for all W in capital W. And so the way we compute it is if we proved this theorem before the break. So if I want the orthogonal complement of the row space of a matrix, that's the same thing as the null space. And because transposes switch the roles of rows and columns, if I want to take the orthogonal complement of the column space, I take the null space of A transpose. Okay? And we had proven that before the break. Okay? And so what that means is that if I want to talk about an orthogonal complement of a subspace W, and I've got a basis, I can just put that basis into the rows of a matrix, and then compute the null space of that matrix, and I've got the orthogonal complement. And we saw examples of that before. Okay. The other thing we want to combine this with is talking about projections. And that's also how we can encode information about angles into the dot product. Notice that when we do the projection here, there's no cosine of theta. If you're looking at this geometrically, you'd think of that as the hypotenuse of a right triangle, and this length here would be the length of the hypotenuse times cosine theta. But here we can do it using dot products. And the thing to remember here is that this expression here looks somewhat complicated, but it's just a scalar, right? Even though there are 4 vectors in that notation. It just reduces to a scalar. The top is a scalar because it's a dot product, the bottom is a scalar, and so you end up with a ratio there. So it looks more complicated than it is. Remember, if we're projecting onto the vector u, I have u in the denominator here, okay, u dot u. So that's helpful to remember. So for example, one of the things we wanted to do is to find the projection of v onto the span of u complement, okay? And if we go backwards here for a minute, the thing to notice about that is if this is u, the span of u is this line here through the origin. And what we're looking for is projecting v onto the orthogonal complement. But notice here, this leg of the triangle is orthogonal to u. And so what we're really doing is projecting v onto this red line here. Right? And there's a way to do that in terms of, if I look at the projection of v onto u, right, then if I take this vector and I add that vector to it, I get v. So by the same token, if I took v and I subtracted off this vector, I get something in the orthogonal complement. I get this red line. Okay? And so that's the calculation strategy we're going to be using here. So first thing we do is project v onto u, okay, and I get that light blue line. Okay? Again, this is just a scalar, and this is going to be, when it reduces, it's going to be 2/3. Okay, and so to get a vector orthogonal to u, again, we just take that difference and we get that red line. And so here's u, here's the projection of, I'm sorry, that's v. We subtract off the projection onto u, and we get an orthogonal complement. And if you notice, if I take the dot product of u, okay, with this vector here, I'm going to get 0, right? So I get negative 2/3 minus 8/3, so that's negative 10/3. All right. I get 6, right, which is 18/3, so that means I have 8/3 left, and then when I look at this, I get a negative 8/3, so I get 0. So I get exactly something orthogonal to u, right, which is exactly what I want. All right. So you can check by doing that dot product that it's, so it has to be in the orthogonal complement of the span of u. So what we're really interested in, really what we want to do is get orthogonal bases. And so first we want to define what we mean by an orthogonal set of vectors. Okay, we extend the idea of orthogonality to any set of non-zero vectors. And what we want to do is we want to say a set v1 through vk is orthogonal if they're mutually orthogonal. In other words, if I take any two different vectors in the set and I take their dot product, I get 0. And as we saw, because it's non-zero, if I take a dot product of VI with itself, I should get something non-zero because V is non-zero, VI is non-zero. We're also going to add an extra condition here. We're going to say that a set is orthonormal, first if it's orthogonal, but also if all the vectors are unit vectors. So what that means is that the length or the magnitude of each vector is 1, so that when I square the magnitude I get 1. And one way to look at that is saying by vi dot vi has to be 1. Okay? And so an example of an orthogonal set would be something like this 1, 1, 1, 1, 1, negative 1, negative 1, negative 1, 1, negative 1, negative 1, 1. And you can check if I take the dot product of this vector with either of these two, it's going to be 0. And when I take the dot product of these two vectors, what do I get? I get 1, 1, negative 1, negative 1. When I add it all together, I get 0. So it's mutually orthogonal. But it's not orthonormal. And if you take a look at this first vector, and you take a look at the dot product with itself, what are you going to get? You're going to get 1 plus 1 plus 1 plus 1, which will be 4. Okay? But it says for orthonormal, I need to have this condition that the dot product with itself has to be 1. Notice if I change it here, so that this is going to be 1 half, 1 half, 1 half. 1 half squared is 1/4. So I have 1/4 4 times, and I get 1. And the same thing happens in these two situations, here and here. So that's when we say orthonormal. So normal just means that I have unit vectors instead of just orthogonal set. So both orthogonal and unit vectors. So the nice thing about orthogonal sets is that if I have an orthogonal set, I know it's linearly independent. I do not need to check that. Okay. And let's take a look at the proof of this. And so let V1 through Vk be an orthogonal set of non-zero vectors. Okay. I want to show it's a linearly independent set. So the very first thing I do is set up my linear independence equation here. Okay. So C1 V1 plus C2 V2 all the way through CK Vk equaling 0. And what do I need to do? I need to show that all of these C's are going to be 0. So here's the trick. For any I take Vi dot this vector. Well, this is going to be Vi dot 0 because all I'm doing is taking Vi dot both sides of this equation. And anything dot 0 is going to be 0. So I know that's true. From my algebraic properties, I can distribute the Vi, factor out the constants, and I get this expression here. So what I get is C1 times this scalar plus C2 times this scalar plus all the way through CK times this scalar is equal to 0. But the thing is we have an orthogonal set. So that means if Vi is 3, V3 dot V1 has to be 0 because it's orthogonal. And so what happens is every time I've got something different than I, this dot product becomes 0. And Vi dot Vi can't be 0 because it's a non-zero vector. Okay. And so when I reduce that, all of these things cancel. All these terms cancel except for 1. And so what I get is that this last term is Vi dot Vi is equal to 0. And that tells me since this term is not 0, that the coefficient has to be 0. Okay? So I write this. Since I was arbitrary, we get V1 through V2, V3, all the way through Vk is linearly independent. Well, why is that? Let's revisit that. So what I do is let I equal 1 in this expression, and then I get that C1 is 0. Then I go and do C2, and when I is equal to 2, and get C2 is equal to 0. When I is equal to 3, I get C3 is equal to 0, and I keep going until I get all the C's equal to 0. And so it's automatically linearly independent, which is great. All right. And so any orthogonal set of non-zero vectors is linearly independent, and any orthonormal set is linearly independent because an orthonormal set is also orthogonal. We say a set B is an orthogonal basis if it's both a basis and an orthogonal set. Okay? And these are the ones that we really like, and these are useful for projections. All right? We say an orthonormal basis is a basis that's also an orthonormal set. So, for example, here is an orthogonal basis of R4. And how do you check it's a basis? Well, I guess by our theorem, we don't need to do much. We just need to check that it's orthogonal. And so all you do is take lots and lots of dot products and show that this thing is orthogonal. By our theorem, it's linearly independent. Since R4 has dimension 4 and there are 4 vectors, by theorem 412, that means it's also a generating set, so it's also a basis. All right. If I do this, and I make all of these vectors unit vectors, then this is an orthonormal basis of R4. So the nice thing about orthogonal bases is you can represent arbitrary vectors as a linear combination of the orthogonal basis elements fairly easily, and so you can get coordinates that way fairly easily. In particular, let B1 through Bn be an orthogonal basis of Rn. Let V be arbitrary. And how do I express it as a linear combination of the B1 through Bn? Well, all right, so let's take a look and do a product similar to what we did in proving our previous theorem. If I want to express it as a linear combination, I write V is equal to C1, B1, C2, B2, on and on, right? And C1 through Cn are going to be the B coordinates in this case. So for any j, what I can do is I can take V dot Bj. The nice thing is that the B's are orthogonal to each other. So I can do the same trick and distribute the Bj across this sum here. And what do? I get a whole bunch of, I get actually n different dot products. But the thing is, almost all these dot products are zero, except for maybe somewhere in the middle here where I get Bj dot Bj. And so, so all of that just reduces to V dot Bj equals Cj Bj dot Bj. And since B is J is a basis vector, you know this dot product here is non-zero. So I can solve for Cj, and it's just going to be this expression, and it's going to be a scalar. So instead of solving a system of linear equations, all I do is take this dot product. All right. Notice that this is really, if I take the Cj here, put it up here, it's really just a projection onto Bj. Okay. So this summarizes in the following theorem, let B1 through Bk be an orthogonal basis of a subspace V of Rn, and let V be an arbitrary vector in that subspace. Then I can write V as a linear combination of the B's just by taking this dot product, right? And so this is what I said before. This is just the projection of V onto B1. This is just a projection of V onto B2. This is just a projection of V onto Bk. Right? And so all I'm doing is projecting onto the individual basis elements. I cannot do this if B is not an orthogonal basis. And this is the power of the orthogonal basis. It means I don't have to solve a lot of systems. I just need to take lots of dot products. All right. So note when B is an orthonormal basis, right, all the denominators in the above expression become 1, so this expression just simplifies here. Okay? So in particular, what happens is that becomes 1, this becomes 1, all the way through until we get that to be 1, and so I can get rid of the denominators, and it just reduces to this expression here. So that's orthonormal bases are kind of nicer. In practice, though, I usually find that when you're doing the computations, we'll see when we create some orthonormal bases, it creates some denominators that you need to carry along, and it essentially reduces to this anyhow. So I really say just follow this form for whatever you need. Okay, this theorem 5. Okay, so let's revisit these orthogonal projections again. Okay, so here's our diagram we started with to give us our intuitive notion projecting V onto U. All right, we've got the formula here. Okay, and what we have in this case is if I take V and I subtract off this light blue vector here, I end up with something that's orthogonal to U. Okay, so we throw in that formula, V minus a projection as orthogonal. Okay. So what we want to do is we want to generalize this in terms of creating orthogonal bases in creating the Gram-Schmidt process. Okay. So since we want these orthogonal bases, if W is a subspace in Rn, we want ways to find the orthogonal bases. We have some sense as to how to find a basis for W. And what we want to do is we want to take that, an arbitrary basis, and transform it into an orthonormal basis using the Gram-Schmidt process. And we will see that soon. And so we've got a way to do that in a systematic way. Okay? And that way we can always find orthonormal bases. Okay? And the advantage again is that we can easily express any vector in our subspace as a linear combination of these basis elements just using dot products. Okay? And so we can use those coordinates easily. Okay? And in particular, when B is an orthonormal basis, we have this nice expression where all I'm doing is just taking the dot product for each basis vector. But again, that's orthonormal where I'm guaranteed to have unit vectors. Okay. All right. So one of the things that we want to ask is, well, what about vectors outside of W? Okay. What's the best we can do here? If V is not in W, how can we find the best approximation of V in the subspace W? So finding the closest vector in W. Okay. And this is where we look at orthogonal projections onto subspaces. And this is sort of like projecting onto vectors, a little bit more general. And so let's, in the case of lines, we have that same old projection formula again. Okay. So when we look at orthogonal projections onto a subspace, though, let's take a look at this diagram here. All right, and if I want to project V onto the xy plane, what do I want to do? I want to take that, I want to drop an orthogonal in this case, and I get that W is my best approximation. Okay, and we call that the orthogonal projection of V onto W. You can think of this if there's a light directly above, that this is a shadow cast, so that you have W there. Okay. So how do we find orthogonal projections in general? Okay. And what we want to do is we want to note that every vector V in Rn can be written uniquely as a sum of the form V is equal to W plus P, where W is in my subset and P is orthogonal to every vector in W. So it's going to be in the orthogonal complement. Okay. And the question is how do we find those things for given examples? Okay. And this is where we use orthogonal bases and orthogonal complements. And so here's theorem 8, and this is a nice theorem here. It says that for any vector in Rn, if W is a subspace, we can find a W in my subspace and a P such that V is equal to V plus P, V is equal to W plus P, and P is orthogonal to every vector in W, so it's in the orthogonal complement of W. Okay. And so furthermore, if I have an orthonormal basis of W, then we have W is equal to this expression here. So that means P is just going to be V minus this expression. Okay? And that's how the proof goes. All right? So, so one of the things we haven't shown yet is there always exists an orthonormal basis. We'll show that using the Gram-Schmidt. But let's assume we have an orthonormal basis, and then let W be the answer given, right? And let P be V minus W. What we want to do is we want to show that, well, V is going to be W plus P, so we want to show this condition. But that really is just rewriting this equation here. The hard part is just showing P is orthogonal to every vector in W. So condition 1 is satisfied. To show condition 2, what I want to do is I want to show P is orthogonal to every x in W. All right, so we take an arbitrary x. Then I know I can write x as a linear combination of my basis elements. Okay, and so v dot x is going to be v dot this expression. Using the properties of the dot product, I distribute v so that I get the dot product with each one of these. And if I do w dot x, well, I put in this expression for w. Okay. Right? Because w up here is given by that expression. So I just substitute that in. Now, this is kind of like multiplying out using a FOIL method, and what we get is I can write it in terms of the sigma notation. Right, here are all my coefficients given, let's do it here, given each one of multiplying the C's here, the coefficients here, with the coefficients here, and then I have the dot product of B1, 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 B2, and on through that, and that gives me all of these. Of course, the thing is that the only time that's not 0, because B is orthonormal, is when I is equal to J. And so while this looks like a mess, it reduces to just V dot BI, and since it's orthonormal, I've got BI dot BI. I've been sitting here too long, so the lights went out in my office. So I get BI dot BI, but this is orthonormal, so this is 1. So that just becomes a 1 right here. Okay? And all I'm left with is this expression, but that's just V dot x. Okay? So V dot x and W dot x are the same, give the same answer. So if I take P dot x, that means I take V minus W dot x. I distribute this using the properties of the dot product. Since these things are the same thing, it's 0. So P is orthogonal to every vector in W. Okay. So this is going to be, tells me that every vector in Rn can be written as something in W plus something in W per. Okay. So for example, here, we talked about an orthonormal basis with a 1/2 here. I've got W being the span of that, and I want to project V onto W. Okay. And so we use we can use this projection formula. Okay. And that's just a matter of taking dot products. And so what I do is I take V dot B1 to get 6, V dot B2, -3, V dot B1, that should be B3, sorry, B3 to get -2. And so I go ahead and just take that linear combination, add it all together, and I get my projection. Okay, 1/2, 5, 7, 11. So taking projections becomes very easy. And so one of the things that was key in, and I guess if I wanted to, for what it's worth, is that if I want to get my p vector, all I do is subtract the 1/2 of 1, 5, 7, 11 from v 1, 2, 3, 6 to get exactly what that p vector would be. All right, and it would be I would have, yeah. So that demonstrates theorem 8 there. Okay. So the Gram-Schmidt process generalizes the above idea to create orthogonal sets of orthogonal vectors. And so, as I said, theorem 8 depends on the ability to create orthonormal bases. So this is how we do it in general. And it generalizes the idea of that triangle we had shown where we project V onto U, okay, and then want to get that red line. And so here's the Gram-Schmidt process, theorem 6.6. Let V1 through Vk be a basis for a subspace W, and we want to transform it into an orthonormal basis. First, we translate it into an orthogonal basis. And so I say, all right, U1, let's get a starting point. Make that V1. U2, what I want to do is I want to project my second basis element onto U1 and then subtract it so I get something orthogonal to U1. Okay? And so I take V2, my second vector here, and subtract the projection of V2 onto the previous one. Now, what I want to do the same thing for V3. Now, since U1 and U2 are orthogonal to each other, when I project onto the span of U1 and U2, all I do is project onto the vectors individually. And so what I'm doing is I'm subtracting off, in this expression, the projection of V3 onto the span of U1 and U2, right? And thus I get something that's orthogonal to that plane, right? And what I do is I keep doing this all the way through. But notice that here I'm using U1 and U2. But U2 is not what I started with here. U2 is this whole expression, okay? So I can substitute that in for U2 if I want. It becomes a huge mess. It's better just to do it step by step this way. And then I can keep going and do this over and over again, adding more and more vectors as I go. And notice what I'm doing is I'm subtracting off the projection of Vk onto the subspace spanned by all the vectors I've created above. Okay? And then what I get is an orthogonal basis. To get orthonormal, all I need to do is divide each one of these vectors by its magnitude. And so we go ahead and let's just consider an example before going through any type of proof of this. So consider the basis here. It's a basis of R4. You can check that by putting it into a matrix and taking its reduced row echelon form. What we want to do is we want to transform it into an orthogonal basis. Okay. If I do that, the first step is easy. It just says, just follow the process. It says for the first vector, just write down the first vector. Okay. The second one, we need to project this vector onto this vector here. Okay. And then subtract off the projection. And so what we do is we use that second vector, 1, 2, 0, -1, subtract off the projection onto 1, 1, -1, 1. Okay, when I do that, by taking the dot products, that's going to be dot product at the top, it's going to be 2. The dot product at the bottom is going to be 4. So I get a nice reduction there. And so I get my second orthogonal vector to be 1/2 times 1, 3, 1, -3. Now, since this is a basis and everything along the line of U2 is orthogonal to U1, I usually do this extra step and just clear the denominator. All right. Well, okay, I guess I haven't this time. So I've got U1 and U2. Okay. Yeah. All right. So I clear the denominator. And so I can just take U2 then to be 1, 3, 1, -3. Now this is for an orthogonal basis. This is not orthonormal yet. We're going to do the orthonormal step at the very end. Okay. And so I try U3. And the thing is remember I take this vector here, okay, but instead of using these two vectors, I'm using my new vectors here. So I'm using this as my U1. I'm using this as my U2. And I've got to use the modified vectors in this formula. Otherwise, I may not get something that's orthogonal. And so when I do that, I take the various dot products. I get my coefficients. First one will be 1/4. The second one is going to be 9/20. I go ahead and take that difference, and well, I get 1/10 of 13 -681. Okay. Again, I don't like denominators, so I'll clear that denominator in a minute. And so I have U1, U2, U3 are going to be these vectors. Now you can check that from this point that U3 is going to be orthogonal to U2, it's going to be orthogonal to U1, and U1 and U2 are orthogonal. So I've got an orthogonal set so far, but it's not a basis because I need 4 elements on a basis. So I need to do the very last step, and for Gram-Schmidt, all right, the more steps we do, the more of a headache it is, which is why you like to do it on a computer. And so for U4, we do the exact same thing. We take V4, but again, we use these modified vectors in blue to do the projections. All right, I go ahead and compute the various dot products. I get 1/4 again. I get 7/20 here. And the last one, I get 26/270. All right, and as you go further in this process, these coefficients tend to get, these denominators tend to get larger, these numbers tend to get larger, but it does work. And when I do that, I get this 1/54, -46, 69, 115, 92. And so I've got an orthogonal basis here. It says an orthogonal set, but remember these are now linearly independent. There's 4 of them, so it's a basis for R4 by theorem 412. All right. So how do we transform it to an orthonormal basis? All we have to do is divide each vector by the magnitude. All right, so the magnitude of this is going to be square root of 4. This is going to be 1 plus 3 squared, which is going to be 10. 1 plus 3 squared is going to be 20, so square root of 20 here. These are going to get larger and larger. And so when we do that and do the reductions, it's going to look something like this. Now, as I said before, I tend to try to just deal with orthogonal bases rather than orthonormal bases because I don't need to deal with denominators that look like this. Okay, and then the dot products just take care of everything. All right. So some observations: if W is a subspace in Rn, we can always find a basis for W and then transform it into an orthonormal basis using Gram-Schmidt. So I can always find an orthonormal basis for any subspace. Okay. The advantage is that we can take projections very easily. We can find linear combinations just using dot products. Okay, and so to remind us to find an expression of how to write W in terms of the B coordinates or how to write W as a linear combination of the basis vectors, all I have to do is take the corresponding dot products. Right, and that's very useful for approximations. What about vectors outside of W? So here we go. So how do we get that best approximation? So we make the following definition. Okay. Here we generalize what we did before for subspaces. Here we just do it for a set. Okay. And so as perp is just going to be, for any subset, it's just going to be the set of all vectors orthogonal to every element of S. And so we get this nice characterization, V is an S perp if and only if V dot S is equal to 0 for all S in my set. So for example, the orthogonal complement of the xy plane in R3 is just the z-axis. Okay. And so what we get is the orthogonal complement will always be a subspace. Right? So just as a refresher, prove the three properties of a subspace. Is 0 in there? Sure. 0 dot v is always equal to 0 for every v. So in particular, it's always going to be 0 dot v is going to be 0 for every s in S. Okay. All right. Let u and v be an S perp. That means u dot s is equal to 0 for all s in S, and v dot s is equal to 0 for all s in S. So that means when I take their sum, by the properties of dot product, I can distribute, but each one of these is 0. So I get 0 plus 0 and 0. So the sums stay in that set. Okay. Finally, let u be an S perp, but let alpha be a scalar. Okay. So u dot s has got to be 0 for all s and s. So that means if I take alpha times u times s dot s, all right, I can pull the scalar out by the properties of the dot product. You get alpha times 0, which is going to be 0. So alpha u is also an S perp. And so I always get that this is a subspace because it satisfies the definition. So S itself doesn't have to be a subspace, but S perp always will be. Okay. All right. So if it's a finite set, what do we do? Right? S perp is a solution set of this set of dot products. I can rewrite it as a matrix vector product this way. Okay. And so S perp is just a null space of when I put those vectors as rows. Okay. We're used to putting vectors in as columns. For orthogonal complements, what we actually do want are rows. Okay. So how do we find orthogonal complements? What we can do is we can start with a basis. Okay. And then what we're looking for is that solution of dot products, right? And so what we can do is show that if it's orthogonal to every basis element, then every vector is orthogonal to, it's orthogonal to every vector in W, okay? And again, that's that old trick of just distributing the dot product across linear combinations, okay? And this becomes an if and only if condition, right? In a trivial way, because if this is true for all vectors in W, then it's got, and basis elements are in W, it's got to be true for all the basis elements, all right? And so therefore, W perp is the same thing as the perp of the basis, and we can use this technique to calculate B perp for any finite set. So again, here let W be the span of these three vectors. I like to use these three vectors. It's an orthonormal basis, so denominators are not so bad. And so what we can do is we can put those three vectors in a row, row of matrix, and find the null space. All right. Once we do that, we see W perp is going to be the span of 1, -1, -1, 1. Again, we've got one free variable. We make that t, we solve for the rest, factor out the free variable. And so here we've got ways of computing W perp. We've got ways of doing projections onto W perp this way. All right. And so what we'll do is we'll see how to use some of those projections, but you see the Gram-Schmidt process. We'll prove the Gram-Schmidt process next time. Okay. And we'll see where, and we want to use that to really show how the process of least squares is really a projection process to give the best approximation on a particular span. Hmm. All right, and so I will see you Wednesday then. Thanks.